Welcome. In this session in linear data analysis, we'll explore how we can assess a classification using a confusion matrix, which is also called a contingency table. In binary classification, we have four contingencies. They are two for the data label that is provided by the user, and two for the predicted class that is a quantization of a classification algorithm. What we can do is similar to a truth table in binary logic. If we recall binary logic, we had a truth table, and the way that we'll represent this truth table is we'll call this the data label, and for us this will be either +1 or -1, and this will be the predicted class. And this will either be +1 or -1. And if this was a truth table, these would be the inputs and this would be the outputs, and we would then fill these values in. In the case of a confusion matrix or a contingency table, this is what we fill in. We say if the data label in is +1 and the predicted class is +1, then these are true positive. And if the data label is +1 and the predicted class is -1, then that is a negative, and because the true value is the +1 label, that is a false negative. And if we sum the row, what we get are the number of positive vectors that are provided to us by the user. Turning now to the second row, if the label is -1 and the predicted class is -1, then that is a true negative. And if the incoming label is -1 and the predicted class is +1, then it is predicted to be a positive, and that is a false positive. And the number of false positives plus true negatives are the number of negative instances in the data that the user provided. Now, an important point about a contingency table or confusion matrix is that there are no settled conventions on whether the labels are the rows or the labels are the columns, on whether the class are the columns or the class are rows, whether +1 appears first or -1 appears first. So what we're doing here is we're providing something that's similar to a MATLAB convention. That is, if you use a MATLAB function to ask for the confusion matrix, it will give you these values, and you may actually have to end up sorting them because it's possible that MATLAB will reverse these +1s and -1s. And this is something that, as computer scientists, we just have to acknowledge is going to happen. Now, there are some common names for these terms that we'll use for the rest of this course, and you may find these useful to know. The true positive rate so the true positives are the number that's in that box for the confusion matrix. The true positive rate is written as TPR, and that is the true positives over the positives. So here we're taking TP as the abbreviation for this box, and P for the abbreviation of the sum of this row. And that is often referred to as the sensitivity. So when you read about, for example, a diagnostic test having a high sensitivity, that means that the number of true positives divided by the number of positives is very high. So this number is going to be bounded between 0 and 1, and it's often represented as a percentage rate. So this is also called the hit rate or the recall. The next interesting one is the true negative rate. And the true negative rate, that is the TNR, and that is the number of true negatives divided by the number of negatives. So that is this box divided by how many entries they are. And this is referred to as the specificity. And you can now start to understand that in a very good diagnostic test, it will have a high sensitivity, that is, it'll have a high true positive rate, or most of the things that are coming in as a +1 are being classified as a +1, and then a highly specific test is one where the labels coming in as -1 are being classified or quantized as -1. So highly sensitive and highly specific means that these numbers are going to be very large and that these numbers will be relatively small. The accuracy of a test is this is sometimes abbreviated as accuracy, and that is the true positives plus the true negatives divided by the number of positives plus negatives. That is, if we add these together and divide by the sum of these, that's how accurate the classification algorithm is. A type 1 error, that is the false positive rate. So that can be represented in two ways. One is we simply call that the number of false positives. So the number of type 1 errors that a classification algorithm commits are the number of false positives, which are this box. And if you wanted to, you could look at the false positive rate, which would be this box divided by the sum of the rows. And then a type 2 error, is the number of false negatives. And some authors will add an additional term, which is the precision. And the precision is the number of true positives divided by the true positives plus false positives. That is, they'll take the ratio along the column. And in our work, we won't examine that. So these are the major terms that we have. So the three key terms for this are the accuracy. This is the number of predictions that match their labels. The sensitivity is the relative rate of true positives, and the specificity is the relative rate of true negatives. So with this understanding, let's go through an example or two and build a confusion matrix.